Assalamualaikum and a very good evening to our presents here. Today I would like to present about chapter 3, Torsion. Firstly, the introduction is interested in stresses and strains of circular shafts subject to twisting couples or torques. Turbine exerts torques T on the shaft, this, and then shaft transmits the torque to the generator. Generator creates an equal and opposite torque, which is T. This is the diagram that can make you more understand about the transmission shaft, which is figure 3.1. Okay, next move to the 3.2, which is my topic. This is I would like to emphasize about preliminary discussion of the stresses in a shaft. The formula is net of the internal shearing stress is an internal torque equal and opposite to the applied torque, which is the formula shows above. And then although the net torque due to the shearing stress is known, the distribution of the stresses is not. Then the distribution of shearing stresses is statically indeterminate or must consider shaft deformations. Unlike the normal stress due to axial loads, the distribution of shearing stress due to torsion loads cannot be assumed uniform. This is the figure that shaft subject to torques, figure 3.2 and 3.3. And then figure 3.4 shows that shear stress varies linearly along each radius of the cross section. And then we have a torque applied to shaft produce shearing stress on the face perpendicular to the axis, which is the element in shaft shown in figure 3.5. And then conditions of equilibrium requires the existence of equal stress on the face of the two planes containing the axis of the shaft. The existence of the axial shear components is demonstrated by considering a shaft made up of axial slats. The slats slide with respect to each other when equal and opposite torques are applied to the ends of the shaft. Figure 3.6 shows the model of shaft. And then we see the application in daily life. Hollow shaft in bicycle. You know, this is bicycle. When you ride a bicycle, you transfer power from your legs to the pedal and through shaft and chain to the rear wheel. This is the hollow shaft in bicycle. And then the sample problem is the preliminary design of a large shaft connecting a motor to a generator calls for the use of a hollow shaft with inner and outer diameters of 100 mm. You can see here 100 mm and 150 mm respectively. Knowing that the allowable shearing stress is 84 MPa, determine the maximum torque that can be transmitted by the shaft as designed and by a solid shaft of the same weight. C, by a hollow shaft of the same weight and of 200 mm outer diameter. We have to answer 3 questions from the sample problems. First is solution of hollow shaft as designed. For the hollow shaft, we have J equal to pi over 2 C2 power of 4 minus C1 power of 4 equal to pi over 2, and then we calculate, get the answer 39.88 times 10 power of 6 millimeter power of 4. Using equation 3.9, we write T maximum Tc over J. When we want to calculate the maximum stress, we must use C, and C means that maximum shear stress. So we calculate and we get the answer is 44.7 kilonewton meter for hollow shaft as we design. And then move to the second question is we calculate the solid shaft of equal weight. For the shaft as designed and this solid shaft to have the same solid weight and length, their cross-sectional area must be equal. So you must start from the middle and then you move to the center, and then you calculate the cross-sectional area, and then you get the answer T equal to 23.1 kilonewton meter. And then lastly, hollow shaft as 200 millimeter diameter. For equal weight, the cross-sectional areas must be equal. We determine the inside diameter of the shaft by writing A equal to AC, and then we calculate to get the answer torque equal to 69.6 kilonewton meter. Okay, that's all. Thank you.
From observation, the angle of twist of the shaft is proportional to the applied torque and to the shaft length. We can see from the figure that the phi is at this area. So we can conclude that the phi is proportional to the applied torque and to the shaft length. When subjected to torsion, every cross section of circular shaft remain plain and undistorted. We can see from the figure that the AB is when subjected to torsion, every cross section of circular shaft remain plain and undistorted. And other than that, cross section for hollow and solid circular shaft remain plain and undistorted because a circular shaft is at this symmetry. Cross section of non-circular is a non-axis symmetric. Shafts are distorted when subjected to torsion. Okay, from the figure, consider an interior section of the shaft as a torsion load is applied. An element on the interior cylinder deformed into a rhombus. We can see from the figure A that length this is equal to the angle of twist. So we can get a formula that length gamma equal to rho phi, or gamma equal to rho phi over L. This we can get from this. This is a L, this is a gamma, this is a rho, this is a phi. So when length multiplied by gamma equal to rho multiplied by phi. So we get the formula like that. Okay, using the two equations, we can get gamma max. That can see from this, when gamma equal to rho phi over L, and Y max equal to C phi over L. C is we get from the
3.
okay. Y max we get from the origin figure. That is Y gamma max length and C. This is from the C is a max radius, and the rho we get from the we take out the segment from the origin that we get. This is rho. This is a small radius from the origin figure. So we can conclude that gamma equal to rho over C multiplied by gamma max. For the application, we take out from this figure. This is a turbine, then that side is a generator. So we take out the shaft like this, and we draw diagram before. We can calculate knowing that the torque T is 4.08 kilonewton meter, determine the maximum shearing stress by a solid shaft. This is a free body diagram. So we use the formula from the subtopic 3.4. Torque max is equal to shearing stress equal to torque C over J. J is pi over 2 times C exponent 4. So we substitute the value T equal to 4.08 kilonewton times 0.04 meter and divide by J is pi over 2 times 0.04 exponent 4. So the value is 14.58 megapascal.
In the elastic range. Okay. We know that gamma is equal to rho over C gamma max, and then it multiply both sides with G, which is shear modulus. So G gamma rho C G max. This G is shear modulus. Okay, then we know that this shear is equal to G gamma, then we substitute it to this equation. So T is equal to rho max. Okay, so this is how the formula of the shear strain we get. Okay, our next equation is torque is equal to integration of T dA, and then rho, do you know that this one is equal to rho over C mass. See, integration of rho square if then we get that top is equal to shear mass over C times by G. So this and then that top C over G. This equation. Okay, there's two type of shaft, which is this one is a solid circular shaft, and this one is solid. This is a hollow circular shaft. Okay, we look at this one here, the solid circular shaft. Okay, when the shaft is rotated to right, then the movement of shearing stress will go like this, downwards, which is like this. Where at this point, which is at the point here, is the maximum shear. So this one is point O. To calculate the shear, you know that shear mass is equal to Tc over J. Then J, it will use the formula of J is equal to pi over 2 C times by C, which is C is the radius of the shaft, and then for hollow circular shaft, when it rotates like to the right, and then the movement of shear stress will be like this. Okay, where over here, the maximum shear, and in the here at this point, here the minimum shear. So for hollow shaft, you know that shear mass is also Tc over J. So we use the moment of inertia. J is equal to pi over 2 times by C, which is this one is the radius of outer diameter, and this one is for the inner diameter of the shaft. For example, in this topic, over here we have a shaft. Okay, it states that the shaft of BC is a hollow with inner diameter with 90 millimeters and outer diameter is 120 millimeters. And then the shaft for AB, CD, and DE are solid with diameter D. We don't know the diameter of the shaft of AB, CD, and DE. And then the question states that it wants the maximum and the minimum of shearing stress in shaft BC and the required diameter D of shaft AB, CD, and DE. So it's given here the allowable shear, which is for shaft AB, it states that 65 megapascal, and shear allowable for CD and DE is 50 megapascal. So we start over here. Since the question wants the maximum and minimum shearing stress in shaft BC, okay. BC is equal to 6. BC. Okay. From here, we want to know the torque that applied to shaft BC. So we will calculate it from left to right. So we take 6 kilometer. Since it the torque move to the left, so we assume this as positive. So 6, which is 6 plus, since the torque at B here move to the left also, so we pass by 40. So we get the torque at BC we will get 20 kilonewton meter. It is a hollow, so at this point will be shear of maximum, and at this point will be the shear minimum. And the diameter of the outer diameter is 120. So the radius will be 60 millimeter, and the radius of inner diameter will be 30 millimeter. Then we know that shear is equal to DC over J. Therefore, J is, since it's hollow, use pi over 2 C24 minus C14, which is, this C2 is the the radius of the outer diameter. Zero point 0.06 power of 4 minus I'm sorry, this one, the inner diameter will be 45 millimeter because it states here the inner diameter is 90 millimeter. So we divide by 2, so the radius will be 45 millimeter. So this one outer diameter and this one is inner diameter. So when we calculate, we get 13.92 times -6 and 4. So here we go to T BC times C over G. So let's go top BC is from here 20 kilonewton. So 20 times 5. C is C of the radius of the outer diameter. So it will be 0.06. Then divide by J, which is we calculate over here, which is 13.92 times 10 to the -6. Then we will get 86.2 megapascal. We know that we calculate just now the shear maximum is 86.2 megapascal. So you know that shear minimum is equal to ratio of the shear maximum equal to C1 over C2. So we want to calculate the shear of minimum. So shear minimum is equal to C1 over C2 times by shear maximum. Then you know that C1 is equal to 0.045 divided by C2 is equal to 0.06. Shear maximum is 86.2 times 10 Pascal. Then we will get the shear minimum is equal to 64.7 megapascal. So we solve for question number 1. Okay, for question number 2, it states the question 1, the diameter dip of shaft AB, CD and DE. So we calculate for shaft AB first. Shaft AB, we know that the top over here is equal to 6 kilonewton. The top over here. So, it given shear allowable, which is for AB 65 megapascal. Okay. You know that shear is equal to C over J. Then J is equal to 65. Oops. from here, we can substitute all the value. 65 10 times 10 power of 6 equal to dot 6 times 10 power of 3 times C. We don't know the diameter. So 65 So calculate it, you will get C is equal to 0.039 meter. This is for shaft AB, and then for shaft BC, shaft CD, dot at CD will be, we went over here. So from left to right, 6 kilonewton. We assume that the movement of the left will be positive. So 6 kilonewton meter plus 14 kilonewton meter minus 26 kilonewton meter will be like this, 6 plus 14 minus 26, we will get 6 kilonewton. So torque at CD will be 6 kilonewton meter. Then it gives shear allowable for shaft CD is 50 megapascal. And then same solution as shaft AB. We will calculate DC over J, and guess here 50 times top over here 6, and C, we don't know the value of C, so J is 5 over 2 C4. So when we calculate it, you get C is equal to 76.39 times meter. Then for shaft, PE, we get the torque at CD. The torque at DE. DE. We can, from left to right, so assume a movement of the torque meter plus 14 kilonewton meter minus, because it moved to the right, so it's negative, minus 26 plus 3, we will get 6 plus 14 minus 26 plus 3. So we will get 3 kilonewton meter Again, allowable stress given is 50 megapascal, and we calculate it to C over J, and 50 times 3 times C over J, which is 4. I would like to mention that we use over here, why we use pi over 2 times C4, because it is stated that shaft A, B, C, D, and D, E is a solid circular shaft. So the formula of solid circular shaft will be pi over 2 C. The moment of inertia for solid circular shaft will be pi over 2 C or times C to the power of 4. Okay, so calculate this one, you will get C equal to 38.2 times 10 power of 6 millimeter. So this is the answer to the question B.
MG12006. Okay, this is my subtopic that I will present in my project. Okay, torsion in non-circular member. Right. So planar cross section of non-circular shaft do not remain planar, and stress and strain distribution do not vary linearly. Okay, for uniform rectangular cross section, it is found that the maximum shearing stress occur along the center line of the radial face of the bar and the angle of twist. Okay, as we can see, this is a formula for the shearing stress. Formula for shearing stress. This is formula for angle twist. Okay, so at the large value of A over B, you can see, you can refer the rectangular bar. Okay, we can find A and B. Okay, A is a long length and B is a short length. Okay, from A and B, we can find the coefficient of value where A over B. So if we get the value of A over B, we can refer to our table coefficient for rectangular bars in torsion. Okay, this is our table. So this is a ratio. We can get ratio. This is coefficient 1 and this is coefficient 2. Okay, so this is very here a few examples to find A over B. Whereas how to find 1 over? This is a rectangular bar. This is A, this is B, where A equal to B. Let's say A equal to 0.001, B is equal to 0.001 in meter. So we divide A divided by B. So we get 1. So we can refer the table of coefficient. So 1, we can get C1 and C2. So as we can see, at 5, 10 until infinity, the value of C1 and C2 is same. Okay, this is because the C1 and C2, we get the value same, exactly same. Okay. So also same with 10 ratio 10.0, where the A is very long than B. So let's say A is equal to 100 meter, B is equal to 10 meter. So we divide A into B. So 100 divided by 10, we can get 10. So we refer to table coefficient. So we get C1 and C2. Okay, until infinity, where the value is too large, the value of A is too large. So we can get the value is same. This is for our table coefficient. We must calculate calculate A over B to get the coefficient for rectangular bar that we can apply in the formula of shearing stress and formula of angle of twist. Okay. Then I move to application in real life. Okay. This example of recheck. Okay. This example of recheck in our real life. Okay. So this have two image, whereas is front view, the side is top view. So as you can see, right, given force is 150 kN. The distance of the ratchet is 3 meter, means from A to B 3 meter, and knowing that the G is 20 gigapascal, determine the shearing stress and angle of twist. As we know, the formula of shearing stress is tau allowable equal to torque over C1 AB square. Okay, which is knowing that torque equal to force times distance. So the given force and distance, so we get 45 kilonewton meter per meter. So from the top view, we can take out this rectangular bar. Okay, A and B. Okay, A is a long length and B is a short length. So A, as we know, A is equal to 0.001, B is 0.001 also. So we divide A divided by B, we get 1. So refer to the table of the coefficient, we get C1 is equal to 0.208 and C2 we get 0.1406. So we apply all the information into the formula shear stress, formula of shear stress. So torque C1 A and B square, we know already the value, so we get the answer 260.35 megapascal. Okay, next for the angle of twist, we know that this is formula. So we get from the table, C2 we get from the table. So we substitute all the value given and we get 4.8 radian. Okay, this is example in our real life that can be applied from torsion in non-circular member. There are many examples. I will choose this one as my example in my project. That's all from me. Thank you.
I want to explain how to get the formula to calculate the shear stress of thin wall hollow shaft. For example, we take this figure. Okay, we take a small segment from this figure and we have summation of F equal to 0. FA minus FB. Minus FB because it is opposite FA. So F we replace with the T and shear A. TA shear A minus TB shear B equal to 0. So we equal shear A times T A equal to T B shear B. So shear times T is equal to Q. Q is constant. And then we compute the shaft torque from the integral of the moment due to the shear stress. Okay, for the small moment, the cyclic integral of small moment equal to PdF equal to P shear TdS. TdS is a area for the small cutting and equal to Q PdS. Q is exits from the shear T. Just now we have find the Q, and then Q PdS equal to 2 QdA. QdA we have from we get from the formula area big triangle minus area small triangle. Area big triangle is half times L plus ds times P. Area small triangle is half LP equal to dA. So lastly we have 2ds times P equal to 2dA. A is the area bounded the center line for whole picture. And then from the equation 2 in equation 1, the shear flow, we get formula shear equal to total torque divide 2TA. So the formula we use in application, this application. Okay, we have two figure A and B, and then the question is extruded aluminium tubing with a rectangular cross section has a torque loading of 2.7 kN. So torque is given in the question. Determine the shearing stress in each of the four walls with A uniform wall thickness of 4 mm and wall thickness of B is the 3 mm on A, B and CD, 5 mm on CD and BD. Okay, solution for A. For question A, we have thick 4 mm and 4 mm. For question B, we have thick different thick 3 mm and 5 mm. And then we solve for the question A. First, we find the area 60 mm times 100 mm. So we get 6000 mm squared. To find shear, we must find Q. So we find Q equal to total torque over 2A. Total torque just given in the question, 2.7 kN. So we just substitute in the formula. We get A equal to 6000 mm squared. So we just substitute. Then we get value 225 10 to the power 3 Newton per meter. So to find shear, for A, we substitute the value we get just now. The formula is Q over T. Okay. And then Q, we have okay. We substitute the value we got just now. Q equal to 225 10 to the power 3 Newton per meter, and T of the figure is the 4 mm. So we just substitute, we get the value 56.25 megapascal. So for question B, the area same, and then the formula is same so happen. So the shear AB equal to shear AC because the tip AB and AC is same, 3 mm. And then we just substitute. The formula is shear equal to Q over P. So Q same, also same. So we substitute the value 225 10 to the power 3 over 0.003 m. Okay, for AC and AB. So we get 75 megapascal. And then for shear BD and shear CD, 5 mm T for the peak BD and CD. So we substitute the value to the formula 225 10 to the power 3 over 0.005 m. So we get 45 megapascal. Thank you.